So we're going to talk about applications of exponential functions in section 4.6, again limiting some of the section by covering just part of it, the part that's interesting and good for you to know. So here we're starting off, it says solving literal equations for a specific variable. Yes, and it would be nice if I turned the projector on so you could see it. There you go. Oops. Okay, so here we come back. All right. So literal equations are equations that have a bunch of variables in them. And so they kind of specifically ask you to solve for a variable that's in the equation. Like in equation 1, it says solve for the variable x. So the variable x you can see is in the exponent. So we need to figure out how to get it out of the exponent. So what you want to do is you want to solve for this exponential term. Okay, we need to solve for that specific exponential term. So the first thing we need to do is move the t to the other side. So we're going to add t to each side of this equation. So then we have 3e to the exponent of nx equaling 4.2 plus t. So again, the focus is on x and on this term. Now we need to get the 3 off of it. So we divide both sides by 3. So then you have e to the nx equaling this big fraction, 4.2 plus t all over 3. So now the reason this question is in this section is because now is when we have to use a method of solving exponential functions to get the x out of the exponent. And so what we do now is we take the natural log of each side of this equation. So I'm going to take the natural log of each side of this equation. And when I do that, I can use the property that says pull the exponent to the front of the logarithm. So this becomes nx, natural log of e, equaling the natural log of all this stuff, and we would normally put all of this in parentheses once we use the natural log with it. Well, remember the natural log of e equals 1. So really all we have is nx equaling the natural log of all that stuff in the parentheses. And so to get x, the last thing you do is divide everything by n. And so x equals this really hideous rational fraction, but it is nat complex fraction, but it's a natural log of 4.2 plus t all over 3 all over n. And you have solved it for the variable x. Okay, you have solved for x. Okay, and number 2, again, it says solve for x, and so the first thing you want to take note of is this exponential term with x as its exponent, which means you're going to isolate that e to the kx on one side of the equation, and then you're going to take the natural log of it. All right, so the first thing I need to do is move the 100 by adding it to both sides of this equation. So then you get p plus 100 equals 100e to the power of kx. Now we still don't have just the exponential term that's highlighted. We still don't have it isolated because the 100 is that coefficient that we need to get rid of. So divide both sides by the 100. So this becomes p plus 100 over 100 equaling e to the power of kx. So we've isolated the highlighted term, the exponential term, and now to get the variable x out of the exponent, we're going to take the natural log of each side of this equation. And we do that because now we can apply that property which pulls the exponent to the front of the logarithm. So the left side is the natural log of this large fraction, this rational, and the right side is going to be kx, natural log of e. Now we refer back to the fact that the natural log of e equals 1, I'm going to put this in parentheses. So the left side is the natural log of p plus 100 over 100 equaling kx. So what is my last step to come up with x? Divide by k. So we have the natural log of p plus 100 over 100, all divided by k being the value for x. So we have solved specifically for the variable x. Okay, so it's really just giving you some practice with how to solve an exponential equation like that. Again, isolating the exponential term so that then you can use the natural log on that term. All right, so now we get into a financing example. It says, suppose that $15,000 is invested, and at the end of 3 years, the value of the account is $19,356.92. Use the model, use this equation for continuous compounding to determine the average rate of return. So the average rate of return is your R value. All right, so let's see. We have A equaling PE to the RT. Now, it started at $15,000, so that's your P. Your original amount is your P. It grew to the $19,356.92. So that's your A value. That is your A value. So then you have E to the RT, where R is what you're trying to solve for. Now, do we know what T is? Yes, time is 3. So we're having to solve for the R, which is in the exponent, which is why we're going to end up using a natural logarithm. So just as with those examples above, we need to isolate this E to the exponent term. We need to isolate this so that we can take the natural logarithm of it and pull that variable out of the exponent. So what we're going to do now is divide both sides by that 15,000 to get that exponential term isolated. So we have this 19,356.92 divided by 15,000 equaling e to the 3r. And the goal is for the equation to say r equals something. We're supposed to be finding the average rate of return, the interest rate. Okay, so just as with those examples above, we're going to come in here now, and to get the exponent off of the e, we're going to take the natural log of each side of this equation. Then we can pull the 3r to the front, knowing that the goal is to solve for r. So now we have the natural log. Let me change my pen color. Now we have the natural, still didn't get it. There. Now we have the natural log of this fraction, 19,356.92 divided by 15,000. Bless you. Equaling 3r natural log of e. But we know, just as in those prior examples, that the natural log of e is 1. It just equals 1. So now I just need to divide both sides by 3 to get r. So my r value, due to lack of space here, is going to be the natural log of 356.92 over 15,000. All of this, the natural log of that, all over 3 will give me a value for r. And I'm going to pause this so I can put this on the calculator. Resume. So on the calculator, this turns out to be and I'm going to truncate it, I'm going to round it off. So it's 0.084999999, which would be, I don't know, what did they say? Did they say how many decimals to round this to? No, they did not. Okay, so I'm going to say approximately 0.08. So let's go 0.085. So we're looking at 8.5% interest rate. Usually they'll tell you to round off to a specific number of digits. And usually you will have your R converted back to a percent in your answer. Okay? So again, those literal equations, those warm-up questions 1 and 2, were to teach you to isolate the exponential term, divide, then take the natural log of it. Yes?
Why do we not multiply out the 19356 fraction?
Why not divide that first? We want to, because it's going to be a decimal value. It's going to be an irrational number, and so I'm going to wait till the very last minute to calculate it so my accuracy is as close as I can get it. Okay, for greatest accuracy. Okay, so here's another one. Suppose $12,000 is invested in a bond fund and the account grows to $14,309.26 in 4 years. So they give us the model, which means you're going to do continuous compounding again, to determine the average rate of return, which find R. Okay, so find R. So this is very similar to the last example we just did. A equaling PE to the RT was given to us. Okay, so it started at 12,000. It grew to 14,309.26, and it was started at 12,000. E to the, I need to find R, and time is 4 years. So just as in the pattern as before, I'm going to divide both sides by that original 12,000 to isolate the exponential term e to the 4r. Once the exponential term is isolated with no coefficient, a coefficient of 1, then you come in here and you take the natural log of each side. That permits me to pull the 4r to the front. When r is what we're solving for, so that's quite convenient. So this is going to become the natural log of my 14,309.26 over 12,000, equaling 4r natural log of e. The natural log of e, though, equals 1. So now all we need to do is divide both sides by 4 to come up with my rate of return. And again, I'm keeping all of these digits in my calculator so that I have as much accuracy as I possibly can in coming up with this value. And this should come up to be about 0.044. Or in other words, 4.4%. So, just over 4% return over a period of 4 years would increase it by $2,300. All right, so what does Part B say? How long will it take this investment to reach $20,000 if the rate of return continues? In other words, if you stick with this rate of return that we just found, if you stick with it being 4.4% or 0.044, how long will it take your amount to reach $20,000? Okay, so this is part A. This would be part B. So my A equaling PE to the RT, where R is now the 0.044, it says, well, how long will it take for this to reach 20,000, for 12,000 to grow to 20,000 using a continuous compounding rate of 0.044? So now the t is what we're looking for. We're looking for time t. So we do the same process. We lose the 12,000 by dividing it off. So I'm going to have 20,000 divided by 12,000. Now you can knock out the 3 zeros and not mess up any of your accuracy. And of course 20 divided by 12, you can reduce that to 5/3, which is fine. Okay, so the same process. We come in here now, and in order to get the t out of the exponent, we'll use a natural logarithm. Now you cannot use just a common logarithm because the natural logarithm is what you're going to do, so the natural log of e becomes 1. Okay, so my left side is the natural log of 20 over 12, which is what? 5/3. equaling 0.044t natural log of e, where we know the natural log of e equals 1. So this becomes the natural log of 5/3 over 0.044 will give me the number of years. So when you put the natural log of 5/3 in your calculator, hit enter, then divide that number by 0.044, you should come up with approximately 11.61. So about 11 and a half years, 11 years, 6-7 months it would take for the $12,000 to increase by $8,000 based on an interest rate of 4.4% compounded continuously. So you can see this pattern is repeated over and over again. Y'all should be pretty darn good at this by the time we finish today's lesson. Part C, determine the number of years required for the amount in the account to triple under this same rate of return. Rate of return, again, being an R value of 0.044. Okay, so for it to triple, it started at 12,000. So to triple, that means I want it to grow to $36,000. So I started at 12,000. To triple, it's going to grow to 36,000. E to the 0.044t. Now, when I divide by 12,000 on both sides of this equation, which you know now from the pattern, that's what you're going to do, you're going to get 3, the tripled amount on the left side, equaling e to the 0.044t on the right. So if you triple it, that'll be a 3. If you double it, that will be a 2 on the left side. So now that you can see this evaluates pretty nicely, you come in here and take the natural log of each side, and you get that the natural log of 3 equals pull the 0.44 in the front, equaling 0.044t natural log of e, but the natural log of e is just 1. So the number of years it will take for this amount to triple under an interest rate of 0.044 compounded continuously should come out to be, I've got 24.99. In other words, 25 years to triple. Okay, so if they have you triple or double or quadruple, it actually comes out to be, the numbers come out a little nicer. Okay, so that teaches you how to find your rate of return, then how to use the rate of return to come up with how to triple something, or to the amount of time it takes to get the result that you want it to grow into. That's really important, because when you make investments like for retirement, you want to know to figure how many years will it take for your amount invested to reach what you need when you retire. All right. So here's another one. This one is a retirement example. Suppose $50,000 from a retirement account is invested in large cap stock funds. After 20 years, the value jumps up to $194,809.67. So it didn't quadruple, but it almost did, right? From $50,000 to almost $200,000. Use the model to determine the average rate of return under continuous compounding. In other words, if the person has $50,000 and he needs to leave it there for 20 years, he wants to know which bank is going to give him the right interest rate to ensure it grows that much. Okay, he knows how much he wants to grow into within 20 years. He just has to go someplace where they'll give him that rate of return. Okay, so we're still back into this continuous compounding equation. This time we grow into almost $200,000. So we're trying to find R this time. We know we're looking at a 20-year investment. So the first thing I do, what is the first thing I do? Good. Divide it by 50,000. So you isolate the E term. Then you come in here and you take the natural log of each side, which will bring that 20R to the front. So you have the natural log of all these lovely numbers, 19,000 number and the 50,000, equaling 20R natural log of E. Natural log of E is a 1, so now divide it by 20. Okay, and I show it's about 0.068, so 6.8%. Okay, 6.8%. Okay, so that's his computations. But then he says, well, man, 20 years is a long time. Rather than almost quadrupling, how long would it take it to double if I did hold into that 6.8% interest rate? Okay, that's a common thing. How long will it take for my money to double? That's a common desire. Okay, so if we started with 50,000 for it to double, it would grow to 100,000. And our R is now 0.068. So now how many years, rather than quadrupling, how many years would it take it to double? So if I divide both sides by 500,000, it will be 2, doubling amount. Tripling was a 3, doubling is a 2. Now take the natural log of each side. So I have the natural log of 2 equaling 0.068t natural log of E, where the natural log of E equals 1. So the number of years to double is the natural log of 2 over 0.068, which I come up to be 10.19 years. So about 10 years to double. At that rate of return. At that rate of return. That many years to double at that rate of return. Okay, really good numbers, really good applications. Okay, important stuff when it comes to retiring. Okay, now this is some interesting stuff. Those of you who like biology, this will be right down your alley. Okay. All right, exponential growth and decay. We apply an exponential decay function to determine the age of a bone through radiocarbon dating. Animals ingest carbon through respiration and through food they eat. Most of the carbon is carbon-12, an abundant and stable form of carbon. However, a small percentage of the carbon is an isotope carbon-14. The rate of carbon-14 to carbon-12 to carbon-14 is constant for all living things. That rate, that ratio is constant for all living things. When an organism dies, it no longer takes in carbon from the environment. Therefore, as the carbon-14 decays, the ratio of carbon-12 to carbon-14 changes. Scientists know that the half-life, okay, how much time it takes for something to decompose to half its original size, the half-life of carbon-14 is 5,730 years, and from this they can build a model to represent the amount of carbon-14 remaining after T years of death. All right, so here's an example taken straight from the book. It says carbon-14 has a half-life of 5,730 years. write a model, and this is just like our A equaling PE to the RT, but they're using Q's. And Q sub zero is sub-zero always means initial amount. So that's the same as our original equation, but they're using Q's and they're using function notation. Write a model to represent the amount of carbon-14 remaining after T years if no additional carbon is digested. So here's the solution. Here's the original equation. So if it's going to be half the size, you put 0.5 of the original amount, which just turns out to be 0.5, equaling the exponential equation. So just as when we tripled, this was a 3. When we doubled, this was a 2. When we half, this is a 0.5 equal to our exponential term. Then they take the natural log of both sides, and they skipped some steps there. But we know that the natural log of E pulled the exponent to the front. And then they come up with this constant that belongs in the exponent of the original equation. Okay, there it is. So this new equation would be like our A equaling PE. Instead of an RT, it's that K value of that 0.000121. So they've created their equation. So then part B up here says, an archaeologist uncovers human remains at an ancient Roman burial site and finds that 76.6% of the carbon-14 still remains in the bone. How old is the bone? So they go to this equation just created, and they say 76.6% is left, which in decimal is 0.766. So over here, they get their 0.766 equaling the exponential term. They take the natural logarithm of each side, divide, and come up with 2,200 years. Okay, 2,200 years. So the age of the bone is 2,200 years old. That's how archaeologists determine the age of things that they find that they're digging up, right? So pretty cool stuff. All right, so don't let this function notation disturb you, okay? It's just like A equaling P. Use this function to determine the age of a piece of wood that has 42% of its carbon-14 remaining. Okay, we can go back to ours if you want to. If y'all don't like that, you can use this one, right? If 42% is remaining, then 0.42 will equal E to the RT. Now, the R is that number they just gave us that they found in that example that I pulled straight from the book, which is that negative value. Wow, bless you. So this is that negative point. I think there were 3 zeros. Yeah, 0, 0, 0, 1, 2, 1. There it is. Okay, so we know the process. We've been doing it so many times now. Take the natural log of each side, and then you get the natural log of 0.42, 42% remaining, equaling the negative 0.000121t, natural log of E, where the natural log of E equals 1. Then we divide both sides by that negative number that they figured for us. And that will be our time, the number of years. Okay, so if you plug all that in, I came up with, what did I come up with? Did I do this? Yes, I did. Okay, wow. Okay, when I put this natural log of 0.42 divided by the negative 0.000121, I came up with 7,169.43 years. Wow. 7,000 years old. Does it? Round to the nearest 10 years? Oh, okay. Well, if I round it to the nearest 10 years, it'd be 7170, right? You be sure you enter the natural log of 0.42, hit enter, then put divided by. And there's one more here. Here's another. Sample collected from cave paintings on an archaeological site in France shows that only 2%, not much, oh my gosh, only 2% of the carbon-14 still remains. Use the model, that model. This is kind of like our A equaling PE to the RT, but they're using Q's. It's in function notation. How old is this sample? Okay, so if it's only 0.02% left, then it's 0.02 equal to our exponential term. This is bound to be a bunch of years if only 2% is left, right? Okay, so now to take the natural log of each side, which is going to pull this exponent to the front. So I have the natural log of 0.02 equaling a negative 0.000121 t, natural log of e, which they're dropping off because the natural log of e equals 1. Now divide both sides by the 0.000121, and you will get your time, which came out to be 32,330.77 years. But it does say round to the nearest year, so it'd be 32,331 years for it to decompose to 2% of the amount of carbon remaining. Carbon dating. I know y'all heard those words, carbon dating. This is what they're doing. This is the carbon dating step. Okay, so pretty neat applications. Again, this is only like a third, maybe half of this section 4.6, which is all you're going to see homework on anyway. But this should have you set up and ready to go.